All right, welcome back. This is our last new lecture before we review for our exam. This is section 1.4, approximate linear relationships. So far we've been doing exact, which means it makes a perfect line, but now this is going to be approximate. Okay, so it's not going to be perfect, but it's still going to look linear. Okay, it's still going to go generally in a line. So problem 1 here says the average ticket prices for the top 50 grossing concert tours are shown in the following table for various years. Let P be the average ticket price in dollars at T years since 1995. Sketch a scattergram of the data and draw a line that comes close to the points of the scattergram. So first create a scattergram. We have our table. I got a little bit of a head start. So I put my title, labeled my axes, and got some numbers in there. Okay, so years since 1995 across the bottom. I counted by ones, and I only labeled every fifth one just because I thought that was sufficient. And up the side, I saw that eventually I'd have to get up to 85, and when I happened to count it out by fives, I could see that it would all fit, so I just went with that. But then I only labeled every other one. Okay, so if you want to get caught up, go ahead and hit pause. And then when you do that too, go ahead and take it a little bit further. Go ahead and actually plot those points. Okay, so go ahead and hit pause, come back when you're ready, and I'll work on plotting mine too. All right, so I have them all plotted. So hopefully you agree that that is generally a line, but they aren't exactly perfectly on a line. So that's why it's called approximate linear relationships. Okay, so we have everything labeled. We have our points all plotted. Let's go ahead and draw in a line that comes close to all those points. Okay, so let me pop my ruler up on here. So if I only connected those first two dots, do you see how that line, it would have all those other points underneath the line? That would not be good. Okay, so we want to try to have about the same amount above and below as we can. What do you think about that? Good, pretty much just goes through the first and the last. That won't always work. It just happens to be working out this time. I think that looks pretty good. So I'm going to connect it up. And just because I know what's coming, later on I'm going to need to know where this crosses the t-axis, so I'm just going to put that in right now. And 6 arrows. All right, so we have it in there. It says, is there more than one possible approximate linear model? Definitely, right? Because the odds of us all doing the exact same line right there would be very small. So yes, but in general, they're all going to look the same. But yes, there's more than one exact linear model. Okay, so now for D, it says use your linear model to estimate the average ticket price in 2000. All right, so in 2000, so we're talking about years since 1995. Okay, so what would be T for 2000? Go ahead and take a guess and tell me what yours ends up being, okay? So look on your linear model. So remember, this is years since 1995, and we're talking about the year 2000. All right, so years since 1995, that would be, so I'd go to the 5, right? Go to the 5, go to my linear model. For me, I'm thinking about $42. Was yours somewhere close to that? It was probably somewhere between, like, I would guess 35 and 48 or so, somewhere in there. If you're in there, it's totally good. Go ahead and try the next one. It says use your linear model to estimate the average ticket price in 2010. Okay, so go ahead and try that one. Come back when you're ready. So 2010, I'd be looking at 15, right? So I'm gonna go up 15 and then come over. And I'm gonna say low 80s. I'll just say $81. So again, if you're somewhere between like 75 and 86 or so, you're probably good. All right. Next, use your model to predict in which year the average ticket price will be $105. So now we're going to be looking at the other axis, right, at the 105. So go ahead and give that one a try. Hit pause if you need to and come back and let's compare. All right, so my line didn't quite go up far enough, so I'm just kind of estimating here. Probably would have crossed about there. So I'm getting at about 19, which is a little bit different than what I got last time I did this. Last time I got about 21, but that's okay because all the models are different, right? So I'll go ahead and put in about 19 years. But it says in which year. So remember that it's 1995 plus whatever you got, which was probably somewhere between like 17 and 24 or so. So 1995 plus the 19. I'm looking at the year 2014 for mine. Next, is it possible to have a better approximate linear model with fewer points on the same line than an approximate linear model with more points on the same line? So yes, it is possible. It seems kind of weird, so let me sketch a rough picture over here for you. Okay, so I just put a bunch of random dots right here. Now, what if first, what if I did this line here? We'll just call that number 1. So that's my first line. How many points does that go through? I went through no points. Okay, now the second one, what if, let me go back and try that one more time. I'm trying to go through 2 points. So there's a point and there's a point. So there's my linear model. So that's number 2. I went through 2 points. So the question asks, is it possible to have a better model with fewer points than a model with more points? So I would say that my number 1 that went through no points was a better model than the second one, right? That second one, I went way off. All right, so we will say, yes, definitely possible. I'm also just going to write that we just want to go with the trend here. Next one, H. Does the linear model give us exact data points or an estimation? What do you think? It's just an estimation. And again, I'm just going to write follows trend. Okay, for I, it says the error in estimate is the amount by which the estimate differs from the actual value. For an overestimate, the error is positive. For an underestimate, the error is negative. All right, for J, it says in part D, you estimated the ticket price somewhere around $42. The average ticket price was $45. Calculate the error estimate. And was it an overestimate or an underestimate? So we're just going to find the difference. Okay, so if it was actually 45, but we got 42, that was a difference of $3. So we said 42, but it was actually 45, so we were under. So that was an underestimate. So that means that the error, because it's an under, is negative. So we would say that the error is negative $3. Next, in part E, you estimate the average ticket price somewhere around $79 in 2010. The actual was $75. Calculate the error. So go ahead and try this one and hit pause. Actually, I think go ahead and try to finish off all those, okay? So give all those a try. Hit pause, come back when you're ready. All right, so for part K, I did the 79 minus that 75. So we thought it was 79, but it was actually 75. So that's a difference of $4. We overestimated, so the error is a positive $4. Finding the p-intercept, and what does it mean? So let me scroll back up. That p-intercept is where it crosses that vertical axis. So I said about 21. So that would be 0, 21, and that would mean that in 1995, the ticket price was $21. Next, it says use the model to estimate the average ticket price in 1990. This was the reason why I went way far to the left, and I told you because I know what's coming. This is the problem I was talking about. So if we just kind of guessed, let's see. Because remember this here, this 0, that's 1995. So we're going to have to go back 5. My spaces are a little bit big. I think that's pretty good. But you can see it's very small. So this time I think I got 0. Last time I think I got like $5. Let's go with the 0 since it seems to be what my graph looks like right now. So that estimates that the average ticket price was $0. Does that make any sense? That does not make sense. So that leads us to the next question, which says, when a model yields a prediction that does not make sense or an estimate that is not a good approximation, we say that blank has occurred. Remember, we're talking about these linear models. So when something just doesn't make sense at all, we write model breakdown. So in general, it's a good model. However, at this point, we had model breakdown has occurred. All right, that wraps it up. I hope you have an awesome day.